Problem number 6. I give you two planes with those equations, and I tell you these planes intersect on a line. Suppose the point P is 0, y, z belongs to this line. What are y and z? So the two planes are negative 8x minus 6y minus 2z is equal to 3, and 2x plus 7y minus 2z is equal to negative 4. So I tell you the point P is 0, y, z belongs to this line. What does it mean for a point to belong to this line? Well, it has to belong to each of these two planes separately. And what does it mean for a point to belong to this plane? This equation right here, it needs to, when you plug in, x is 0, y is capital Y, z is capital Z, you have to satisfy the equation. So this tells us negative 8 times 0 minus 6 times big Y minus 2 times big Z has to equal 3, which is just negative 6y minus 2z equals 3. And when we plug in x is 0, y is big Y, z is big Z into this second equation, we also have to make this equation true. So 2 times 0 plus 7 times big Y minus 2 times big Z is equal to negative 4, which is 7y minus 2z is equal to negative 4. So at this point, we need to figure out what what y and z are. We need to figure out what are y and z. And we have a system of two linear equations in two variables, y and z. So there's different ways to do this. I'm going to do this with elimination. So if I multiply this equation by minus 1, I get negative 7y plus 2z is equal to 4. And then I'm going to add together, these two equations to get negative 13y is equal to 7. So that shows us that y is equal to negative 7 over 13. Okay, y is negative 7 over 13. So then we just need to plop that into one of these equations, like the first one, negative 6 times negative 7 over 13 minus 2z is equal to 3. If you solve this for z, you end up with z is 3 over 26. Okay, so then what are the coordinates here? 0, negative 7 over 13, and 3 over 26. That is the point that falls on this line. That's the intersection of these two planes with x coordinate 0. So then in part B, says here, suppose that v is a tangent vector to this line, or v2 divided by v1 and v3 divided by v1. So how do we find a tangent vector to this line? Well, let me just draw a picture. So, here is some plane. Here is some other plane, and these planes are going to intersect in some line. But if these planes are going to intersect in some line, that's the line we're trying to figure out. Well, this line has to be orthogonal to the normal vectors of each plane. Right? So each of these planes has normal vectors associated with it, and we can read off those normal vectors just from the equation. The normal vectors just using the coefficients of x, y, and z. The normal vector for the first plane is negative 8, negative 6, negative 2. The normal vector for the second plane is 2, 7, negative 2. These are the two normal vectors here. And so this is really asking us for find a vector that is orthogonal to both of these vectors. So how do we find a vector that's orthogonal to both of these vectors? Take the cross product. So we need the cross product of n1 cross n2. So -8, -6, -2, 2, 7, -2. And so if you take the cross product of these two vectors, I'm going to skip the steps here and just write down the answer is 26, -20, and -44. If you are suspicious of this, you can check that this is in fact orthogonal to both n1 and n2. And so we can use this as our v. V is 26, -20, and -44. So what was the problem asking us for? What's the ratio of v2 to v1 and the ratio of v3 to v1? So v2 to v1 is equal to -20 over 26. v3 over v1 is -44 over 26. I guess those can simplify just a smidge, but those are our answers. You might be wondering, why did we phrase this in a kind of funny way? Well, any scalar multiple, let's tack in non-zero as a modifier there. Any non-zero scalar multiple of v is also going to be a direction vector, a tangent vector to this line. But if we do v2 divided by v1, v3 divided by v1, those will have to be defined in this, like there's unique ways to express that.